Okay, we have a nice demo for you today. It consists of two ways to do model testing. It's shaker based and hammer based, exactly as we talked last week. We will start with the shaker, but we will start with. I mentioned something briefly that the setup depends also upon the time that you have to set up and to disassemble your test, right? So just take a look here. This is a very modest setup with eight channels, but appreciate the mess here. Appreciate the cabling and all the stuff that's going on. So just imagine how it will look like with 50, 100, and 1,000 channels. Okay, so a lot of stuff going on here, and you need to first of all make sense of all of it, of all the cabling, all the sensors, and also it takes time to set it up and to disassemble. Okay, we will start with this. This is a simple beam. I guess I should stand on behind there, right? Yeah. We'll start with the simple beam because everyone starts with simple beam. It's like hello world in model testing. We have this beam which will vibrate laterally. Okay, it has 4 sensors, 4 accelerometers. Okay, so it actually has five nodes. One node is not moving, and 4 accelerometers, and we have a shaker that is connected to this node. Okay, so this is. You remember how this point is called? The point when we excite and also measure the response. You don't. So this point is called drive point, and with nothing else, all the mathematics behind this this approach, you simply have to have drive point measurements. Okay. Everything else you can skip, but you have to have drive point measurements. Okay, and what we're going to do, we're going to excite this beam broadly. We're going to excite it with random noise from 10 to 600 Hertz, and we'll see what happens. So for all of you that's here, I cannot project this there, so please take a look at my screen. Okay, there are not a lot of people, so it should be doable. I want you to look at these two plots, and these 2 plots are already calculated FRFs, so frequency response functions between one of the responses. For example, this one is the drive point FRF, and this one it's the tip point against the input. So you see that you already noticed that where are you going to see your natural frequencies, right? You see the peaks. So the peaks will be somewhere where your natural frequencies lay. Okay. Now I also mentioned something that you never do measurements without averaging. Notice the noise here. So the program, it collects data and averages it. So at first you have a lot of noise, but once you collect it and average it, the noise goes away. So you never do like single excitation and derive your modes. Okay. Now we're collecting data. We did this. Now let's see what kind of results can we expect. So the way it goes, the system will collect data, input-output data. Then it will fit to your measured FRF. It will fit mathematical function, and only from the mathematical function it will get your modes and frequencies. Okay. This is done just to get you.
And then Sweden has a comment here. Sweden, do you have a problem?
Yeah, the computer turned off and you have to unlock it, so we are going.
Okay, their computer turned off.
Oh, okay.
So we'll continue, and this will be on the recording.
We'll continue, yeah.
Okay, we can listen to you.
Okay.
Okay. Now this is one. Let me show you another one. Sorry, not this. this plot shows you two FRF functions. One of the drive points, the blue one, and the input from here and output from the tip point. So notice that the transitions between peaks can be different, right? But the peaks kind of coincide, right? So it just tells you that it's close to natural frequencies. Natural frequencies are properties of the system, not single points. So if your beam is vibrating at one natural frequencies, the whole beam will vibrate. There is no such thing as separate vibration at natural frequencies. Okay. Now I'll try to make it as small as possible. So not get this. Okay. Next phase into the analysis is called the stabilization diagram. Stabilization diagram simply checks whether your natural frequencies will maintain when you increase the order of the model. For example, if you have function that is quadratic, right?
Who am I speaking with?
This is Bob. Hello.
I think I get the wrong number.
Okay. So think about that. If you have a quadratic function, right? So you can fit polynomial of third and fourth and fifth degree to your quadratic function, right? But the dominant coefficient will be near the x squared, right? So it's kind of the same way it goes here. We are checking whether with increased or model order we will still maintain the same natural frequencies, the same poles.
Yeah, I have
Okay.
a J number. Yeah, that's big.
Okay. The nice thing about doing this way is that you get your output straight away. So this is what does it look like?
Yeah, you probably want to point out the
Yeah,
in the tip
this one. So
No?
this is the tip, and this is the root. So what the shape looks like second bending. Okay.
You guys get that?
You get
So
you get a
first of all,
second.
what's the shape of first bending? Like this, okay. So you see how this is different?
You see there are two nodes here, one node and the second node. Okay.
This is, I've noticed on automobile, where if you have a fender a bar antenna, or the little rod antenna, if you're going like, what, 80, 90 kilometers per hour, this mode usually gets excited.
Yeah, that's interesting. It's not the first one.
It's not the first one.
Yeah.
You'll see this mode if you look. So, but be careful when you're watching this, because you still have to watch the road.
So let's we are going higher. You see, this is we are adding another node here. So this is looks like third bending. What about so notice that sorry. You see, we are increasing when we're increasing with frequencies. We are increasing with the complexity of the shapes. Now, let's go even higher. You see this.
You cannot see the
Right part of the screen.
right part of the screen.
Is this better?
Is that better?
You see the wiggly worm?
Yeah.
I wish I could make it. I can't figure out how you make this bigger.
Okay. So my question is this: what happened between this mode shape? This is third bending, and here. It kind of reduced in complexity. It has less nodes. So what happened? You remember we talked about how many sensors we're using in the beam in our structure, in our test? So here we are missing a few measurement points to add another node. Let's say this is third bending, which is fairly obvious, and this should be fourth bending. So we need to add another arch here, but we don't have enough sensors to see all the whole mode shape. Okay.
Let me add a comment that, so the blades that we work with, I don't have one with me here today, but they're not really cantilever
The
beams.
one yardstick?
Well, we'll do it, make it quick. They're really not cantilever beams. They're more like plates or shells. They're basically a shell. But the lower modes are very much like this cantilever beam mode. So you hear people in meetings say at Pratt & Whitney talking about first bending and second bending, or they also call them first flex or second flex, for example. And then once you get up so high, people's discarding of complex modes because they're hard to describe with like a beam kind of approach. So we use the terminology of beams on blade vibrations a lot, especially for the lower modes.
Okay, so what the information that we can have from here is it's very valuable. First of all, we have the frequency and also the damping, the modal damping of each mode. So I mentioned this briefly, but test is the only way that you can actually determine damping. This is modal damping. Once you know the modal damping, we can transfer it to the physical, to the whole system level. Okay, and for model A, this is something that you can derive the model mass and stiffness from. Okay, so just appreciate the ease that is happening now, and that you don't have to deal with the ancient systems that required you a lot of paper and a lot of accounting for measurements and responses.
And again, all of these modal things that Danny's describing is the rest of the semester we're going to talk about. That's a lot, tell you how useful they are.
Yeah. Oh, any questions about this simple test with our beam? KTH, did you miss something?
No, no, please.
Okay. In terms of the excitation that you did, Danny.
Okay, so with the setup I can do all kinds of excitations. I usually prefer the burst random. Burst random means that it excites random half of the time, and half of the time it rests. So there are a lot of advantages for this. First of all, we are exciting broad spectrum. We are exciting frequencies. Not a single frequency, but in large bandwidth. And another advantage is that the signal itself is periodic. So it's very important for FFT analysis. And later you will talk about windowing.
We already did.
Okay, yeah. So this signal does not require a window. Okay, so you're not altering the signal. So it's very convenient. That said, if you notice that for example I did not excite here the first mode, the first bending. First bending is it sounds simple, but it's actually kind of tricky to excite. First of all it requires low frequency excitation, and it requires to be narrow to have a narrow bandwidth. So if I want to excite it with this beam, it's below 20 Hertz. So I actually need to do something like between 2 and 20 Hertz, and it usually takes more time. It's not suitable for a brief demo.
Your rod there, a stinger.
Oh yeah, the stinger here.
Yeah.
Okay, we mentioned this before. Yeah, that's here. Okay.
We can only go so far.
Okay, this one. You remember that I showed you the shaker, that each model shaker has this sting. It used to uncouple this movement. So lateral, it has very low stiffness. It is stiff only in the direction of the force. So we are looking to excite the natural frequencies of the structure, not the structure with a stiff shaker. Okay, so that's important. Okay, and that's it. Yeah.
So, and then they've already learned ping or impulse testing.
Yeah. This will be the next one.
Is it, you're going to do that?
Yeah.
Okay. All right. And that one. But there's, I mean, you could slowly sweep the frequency and take data, the excitation frequency, and then of course you could use these much better techniques that he's shown.
Yeah. So.
Or random.
Yeah. So you appreciate that. Notice the setup. The setup has 4 sensors and 1 shaker, but the test time was really short. Okay. Now we're going to switch to the ping test or hammer test. This. Okay, I have this handlebar. It is you can appreciate that it's a little bit more complex than the simple beam. Okay. What I have here is this very scientific fixture here. Okay, and only one sensor. Only one sensor, and we're going excited with the hammer. This is our hammer. So the early equipment for model analysis, it contained only 2 channels: excitation and response. So if you wanted to get to test a large structure, you need to tap on different places, different excitation, and yeah, so it's much easier now. So only 2 channels. And we're going to tap on seven points here. I want to show you the model. Okay, so if you look at it, you can you note. Do you see it?
Yeah.
You see the model?
Yep.
So you can see the kind of resemblance of our real structure, right? Okay, and also note that this structure is three-dimensional, very curvy, and my model is really simple. We talked about it last week. We don't need anything complex to show our modes.
And it's symmetric.
Yeah. So this is a simple tapping technique. The thing will trigger. Okay, and this screen will show you time history of my heat and the FRF. Now I'm going to. No, it doesn't like me today. Just a second.
The ding.
No, the ding detects double tapping.
Yeah.
Double hit.
There's an art to hitting.
Yeah. Double tapping is not allowed. Let's try again. Just a second, sorry. Double tapping occurs when you hit the structure, and it usually hits back because it's so elastic. And what it does, it distorts the signal. So
We'd like to be close as an impulse.
yeah, we don't like it. Let's increase this.
So you guys remember the frequency content of an impulse?
Okay, you can maybe show them the test.
Is it infinite, right? If it's a pure impulse, it's infinite.
Oh, come on. Notice that we use 3 tapping at each point to average the signal. Okay, switches. Okay, switches points. Our structure is stiffer, it's less prone to double tapping.
He's now hitting at point 2. There's that point 2.
This is point 3.
Point
It's
three.
just
Okay.
numbering.
Okay.
Now this one is point nowhere to. And the last point. Yep. Finished? Yeah. Okay, so it took longer, but it's not terribly long because the thing is not that big. Now, if you are testing like airplane or car, just notice that the directions of the excitation and the measurements can be different. They're not all pointed the same direction. Okay, once we got the data, they see the screen?
Yeah, but I think if you bring it closer again, they can probably see the details.
Like
This
oh.
closer.
Okay.
There we go.
So once the data is collected, the analysis is pretty much the same. We fit the model into the excited data. You can notice that we have more peaks now, and it's understandable because the structure is more complicated. Okay. Now let's look at the modes. Okay. So first of all, you see the complicated shape. Now, this I can tell you that it needs further testing because you see this wiggling here, and it doesn't it's not in phase with all the structures. So something happened. Maybe one of the double tapping got in. So I will retest this later, but the principles are there.
In terms of mathematically,
Okay.
I mean, what I guess the theory, what Danny's doing, you'll have real mode shapes. There'll be no phase
Yeah.
shift. The only phase shift would be 180 degrees. That is
Yes.
completely out of phase. So,
So-
either 0 or 180. But so he's seeing more like a traveling wave.
Yeah, and just to tell you that testing is never one shot, and that's it. So there are all kinds of data that will help me to determine this. It's more. There are more tools available on site. So just notice here, this mode shape for a second. Let's say that this clamping is a real one, okay? And I'm really interested in the stiffness of this clamp, okay? So to model this, it's either it will take you a year or something with testing, or you can just do a quick test and determine the natural frequencies, and you know that that stiffness will determine your frequencies. So simple model test will save you a lot of modeling efforts. Okay. So sometimes in the industry you prefer to do a simple test instead of modeling stuff. Okay. Now, say more flexible in.
That's a different mode. Then.
That's a different mode. Let's go here. See the antisymmetric, symmetric, antisymmetric. So you notice that this mode and this one are kind of similar. So the question is why? Look at the structure. Look at what might be the reason.
I'll give them a clue.
Yeah.
So, I mean, again, we'll go with theory. If a structure is perfectly symmetric, your modes will be either symmetric or anti-symmetric. There can be nothing else. And then if there's if it's close to being symmetric, then what you typically find is two modes that are close together that I guess usually are kind of similar.
Yeah.
So I guess with that as a clue, how do you answer Danny's question about why would this not quite be exactly antisymmetric or antisymmetric?
Yeah, what Dr. Hilb said is exactly true, and also because this structure will have modes that are vibrating in the vertical direction, maybe lateral. So, but we are measuring only vertical. So there can be a slew of lateral modes into the vertical direction. So that's why you see two modes that are kind of similar, but they may be very different in the lateral direction. We are not measuring them. Okay, and
somebody has to have a question on this.
I hope so.
Sweden or the U.S. here?
Yeah.
Nobody has a question? Somebody be brave enough to answer a question. We give extra points. Mihai, I'm going to ask you a question.
Can you explain one more time why they're like anti-symmetric?
Yeah, there's this. No, there's no. There are antisymmetric modes in the system. There's no explanation why they are there. So we have symmetric, antisymmetric modes, maybe asymmetric at all. No symmetry at all.
Well, I mean, I guess I'd call it a proof that they can be symmetric or antisymmetric. Is what if you were, say, on ANSYS, you would model this, and you're modeling a perfectly symmetric thing. If you want to save yourself some modeling, you can model half of it. Okay, you can model up to the support here, and then what you do is you have to then run it twice. You can model half, but you have to model it or do your analysis twice. Once was the symmetric condition at the middle, where you say you kind of force it to do that, which is true, it has to do that, or you can put an anti-symmetric boundary condition there, which would allow it to do that. So that's, in fact, so if you model it with 1/2 of your structure, the computational time is 1/4. So if you multiply that by 2, you end up with 1/2 again, so you've cut half of your computational time. Now, nowadays, people don't care so much about computational time of finding elements because they run so fast. But that's kind of, the boundary conditions are kind of what answer your question that force it to be symmetric or antisymmetric.
Yeah. So this is more important in when you're modeling planes. So half plane or full plane, it's a big deal. The modeling effort is more complicated.